My name is Connor Tinker. Today we're going to be talking about instrument to inference architectures, and what I want to do today is describe what are the foundations of machine learning as they apply to remote sensing, and how we can derive inferences from spectroscopic data sets. Now, I really want to focus here on the foundations of machine learning and try to describe what neural networks are, what are they and how are they connected, and try to unmask AI a little bit so it feels less like a magic box, so as scientists we can use these tools in our toolbox effectively, and hopefully describe what the math behind machine learning is so that we can better understand how it applies to hyperspectral images. So what you're going to look at here is a multi-layer perceptron or deep neural network, artificial neural network. You're going to be seeing a lot of diagrams like these. You have an input layer, hidden layers, and an output layer. Remember that the notation we're going to be using from now on has the layer on top, the neuron that we're interested in, and the previous neuron on the right here. And it's intuitively kind of simple. All you're really doing is connecting these neurons and multiplying them in a way that's described by this equation here. The weights are the W, they determine the strength between the neurons, the connection strength. The activation value is the intensity of the response of that neuron, and the B is the bias that shifts it. We also use an activation function to bring all of the outputs to a range between 0 and 1. Now what this actually ends up looking like is just multiplication and addition, and these are essentially the foundations of most machine learning networks. When you plot this out, you're really just taking the weight times the activation for each neuron and adding the bias. And this is called forward propagation in a feed-forward neural network. But of course, they don't always look this simple, right? So neural networks tend to have tons and tons of weights with lots of biases each, and that adds up. And I'm very lazy, so I'm not going to be animating all of this stuff for you guys. I'm going to be using 3 Blue 1 Brown. His name is Grant Sanderson. He's on YouTube. He makes really good stuff that helped me learn a lot about this. The demonstration that we're going to be showing is the use of, oh, it got backwards on me, is the use of classification neural networks for handwritten digits. So we're going to be classifying a handwritten digit. And when we break this down, why this is very intuitive is because a handwritten digit is really just a 2D image where each pixel is an activation function, right? And each one of those pixels can become one of our neurons feeding into this network. And when we break that down, the weights are here and the biases are here. And what we do to start this is we initialize them randomly, if the computer wants to. All right, so if we randomly initialize the parameters, it turns out that the results are pretty bad. The loss function is what we use to quantify the difference between the real and the activated values, right? So what you missed there in that animation was that we were putting the handwritten image in and we're getting a bad output. And we use a cost function to average those losses over the entire data set. So all this is saying is, hey, we're getting a generated output, we're comparing it to the real, and we're applying a cost to that. Now what this ends up looking like is we have these 13,000 weights and biases in this function. And what we can do is apply a negative gradient to that cost function to tell us how to nudge those parameters to most quickly decrease the cost. Now this sounds complicated, but we'll simplify it by placing this into one equation where there's one input. And you'll notice that all we need to do is take the derivative to find the minimum. And that really is as simple as it is. We use the derivative of the cost function with gradient descent, which is what we call it, to update the parameters of the model. Now, how do we find the derivative of the cost function? Well, we're just going to use something called backpropagation. So forward propagation and backpropagation are really all you need to know to understand how neural networks are learning. It's a chain rule that computes the partial derivatives of loss with respect to each parameter, and this provides gradient descent, and they call it descent because it's descending, the nudges that it needs to minimize that error. And this feels really weirdly simple, right? Because all you're really doing is comparing the real and the generated outputs, and that's allowing a neural network to learn. It seems trivial, right? And so if we can nudge in the direction that reduces the error, well, then we can do this for anything that we have a real output for. That begs the question, what if there is no real data to compare to? And this really is the most common situation we're dealing with. So I wanted to find some terminology to help out. We have artificial intelligence, machine learning, and within that, neural networks and deep learning, right? A lot of these terms can be conflated pretty easily. I'm not going to go into all of them, but just understand that within all of these, we have supervised learning, which tends to be task-driven, so something like classification. We have unsupervised learning, which tends to be data-driven, so you're doing something like clustering. Or you have something that is a reinforcement learner based. So it's more like a game, and we won't go into that today, but it's a pretty interesting side of machine learning. All neural networks end up looking like these webs of neurons. They just are connected differently and have different numbers of layers. And that's what's really cool is all of this fundamental math can be boiled down into all the different kinds of neural networks that you hear about today. All right, here we go. So supervised learning is when you have an input, your model, and use that model to create a predicted output, and you use a loss function to compare the output and the real. In unsupervised learning, you have your data and some method in order to cluster it. right? And in self-supervised learning, you use your unlabeled data and encoders to build representations of that you then do self-supervised loss with. Now, there's a lot of other types like reinforcement, transfer, federate. We're not going to go into those. We're just going to be talking about supervised learning for now. And the reason is because the classic supervised learning example is number identification. And there's this MIST database which has 70,000 handwritten digits and labels for those digits. And this is why. It's because we have ground truth, right? We have labeled data to work with. And we can use this in a convolutional neural network. Quick reminder, convolution. Let's say you have two functions and you want to combine these functions. You can add them, you can multiply them, or you can apply a convolution to them. Now, this is going to look more easy when we put it in the context of an image. This is called a sliding window convolution. So it's essentially a weighted moving average of the data within that window crossing around the window and kernel can also be nonlinear, right? So how far it's moving is essentially just the stride. So it's just a window of averages moving along your data. This is going to be a little bit easier to see when I put it in the context of an image. So let's say you have this image of Mario. Each pixel is being weighted by about 1/9 for every channel. And the result of that is essentially just a blurring effect, right? And so convolutions are pretty much everywhere that we don't notice them. Another thing that what you'll notice is that if you use a Gaussian kernel, you get a Gaussian blur. That's something that I didn't really realize. A Gaussian blur is just a Gaussian convolution. Convolutions and kernels can also be used to highlight particular orientations. So if you have a vertical kernel right here and a horizontal kernel right here, they'll highlight vertical edges and horizontal edges. So convolutions are really the foundation of image domain neural networks. You use a kernel, you slide it across your image in order to simplify it into some output, right? And what we can notice from this is that shallower layers will tend to learn simpler features like lines, directions, and color. So this is from the AlexNet paper, and this is showing that the first vision of a neural network is really just basic patterns, colors, and orientations. And as you go deeper into that, the deeper layers will tend to recognize complex edges and patterns and shapes. So you can see he's holding up a piece of paper here and it's picking up on the edges of that paper. As we go further in, near the output of the neural network, we're going to start to detect and classify abstract objects or scenes. So this is Welch Labs here on YouTube. He's putting himself in view of the network and he can actually pick out now his entire figure because we're towards the ends of the layers. But to learn what Stephen Welch looks like, the model had to be trained on lots of images of people, right? Labeled images. And this is that multimodal training data that we're talking about. And when we talk about lots of images, I really mean a lot. Modern LLMs are trained on 2 to 15 trillion parameters and tokens, right? So that's a lot of data. Now, we've been talking within the context of a 2D convolutional neural network, right? So we have a 28 by 28 by 1/3 channel because it's grayscale. But most models are really designed to work with 3-band RGB images, right? So you have your spatial dimensions, 95 by 95, and 3 bands. Or if you're like us, you're interested in multispectral data where you have upwards of 50 bands. Or even, and it's going to freeze again. So we can apply 2D CNNs to RGB images because there's enough visible colors to do so, right? You can't mix more than 3 channels without running out of colors. So 2D CNNs are really only capturing spatial relationships. When we're working with hyperspectral data, if we want to capture more than just patterns in that spatial plane, then we're going to want to use a spatial spectral kernel, right? So in this kernel, your bands are across depth and your brightness is the intensity of that pixel, right? So you can build up your spectrum like this through depth. And this is where we can now use a supervised 3D CNN, right? And we call it supervised because when we're doing our classification, we actually know exactly what we're looking for. So these are the 3 classes. We have soil, tree, and water. And we have abundance maps for each of these classes. So I know at every pixel what the actual abundance of each of those spectra are. And that's a lot of ground truth. It's a lot of ideal data. And so in a supervised convolutional neural network that has this much data, it's very possible to get a highly efficient result. I did tell a little bit of a lie here. This is not actually the kernel, that's actually the patch. So in a 3D CNN, we use a patch to ensure that there's pixel context. So a 7 by 7 patch will get all 7 pixels in an area and slide across and get the next 7, right? And within that patch is where you have the kernel. So this little orange stripe there is sliding across, and it is applying a convolution by the kernel, sliding across the patch and applying the learned weights. If you have a stride of 1, remember that stride that we talked about with the convolution, then you have 1 sampling per band. If it's a stride of 2, you are effectively downsampling, right? Because you're doing 2 bands per 1. But for now, we'll focus on a stride of 1. So you use a small kernel to capture the very nuanced spatial spectral variability, and use the patch to capture that broader relevance. There's also learning rate and pooling and epochs and all this other stuff that's not really important right now. But I think it's worth noting that the learning rate, which you might have heard before in the context of machine learning, is just the step size of that gradient descent. So the rate at which we're descending is that learning rate. So this is the Samson data set. It's a hyperspectral image input that we use a lot for these kinds of experiments. And this is the alternately updated spatial spectral convolution by Wang. And this is a really, really good model because it uses a very efficient combination of training parameters to get the output. I did mention that there's a lot of training data involved in this. I'm going to skip through a little bit. But in reality, it's only 130,000 parameters in order to train the model to guess the abundance of certain classes from spectra. Again, we're using a loss function, right? So we're using a softmax cross entropy to increase interclass distance, so the difference between the classes. And we're using a center loss to decrease intra-class distance, so the similarity within the class. And we get some pretty nice outputs, right? And you can see this as the epochs progress, it builds up those maps. But the key here is that AUSSC is making tons of improvement on traditional models to minimize the dependency on ground truth. This is actually a really low number. It's impressive to get a model like this down to 130K. And it's still depending on 200 plus spectra with labels. So it's clear that with even the most ideal and very broad and distinct distinct classes, even a highly supervised, optimized supervised model can't be sufficient if it requires this much effort. And so this seems to be the largest gap with machine learning and hyperspectral images. The training data needs to have all of the variability, the compositional, the physical, the chemical, the environmental, all of the context. And then your ground truth data has to also reflect the inference you're trying to gain. And so if that's the case, then aren't we just recreating the entire field of remote sensing all over again? Right? If I need to do all of this in order to get the ground truth, why don't I just do this to answer the original question? Right? Creating the model feels like more work than it's worth. And this is why we refer to the idea of creating instrument-to-inference architectures. We want onboard, on-demand pipelines that do the identification, detection, classification, mapping, and quantification. Because for machine learning to be worthwhile over traditional spectroscopic methods, it needs to be on board and on demand, right? It needs to replace having to send all this data back and have to, get a person involved in it. It needs to be automated, right? So we don't want to hire spectroscopists to go through all of this stuff. That's the whole point. And it needs to be resource efficient. So when we deploy it, we need to have it pre-trained and low compute, right? So we don't want to be sending GPUs into space. We want to be able to do this all on board efficiently. And it turns out, in order to address these three things, we need semi-supervised, unsupervised, and self-supervised methods, right? So to avoid this whole ground truth problem, there's no way that we could build up models like we did with AUSSC here, right? It would take way too much effort to address every composition in every context, right? And so we need to move away from these supervised methods and into these unsupervised methods. And I'm going to spoil a little bit here because this is the unsupervised models that we've made. What this is effectively doing is domain translation. So we have a low spectral resolution spectra right here as being translated to a high spectral resolution. So it is effectively doing a super resolution of this data. It is filling in the gaps in the data. And this is a fully unsupervised method that we won't be able to go into today, but I wanted to get a little bit of background on how this stuff works so it feels a little bit less like magic and more like simple mathematics, right? So we've established that neural networks are fundamentally just addition and multiplication and a little bit of derivation. It's mostly the scale that brings the magic to the mix, right? Machine learning with hyperspectral data is usually the same methods that we apply with images. It's just an extra dimension, right? It's instead of 3 bands, it's 156 bands, right? And so we're using kernels and 3D kernels instead of 2D ones. And it seems like the largest gap preventing us from using machine learning for hyperspectral images, other than those that just want to sell it to you, is ground truth, right? Because if we're going to solve problems with machine learning, we're going to need to spend a lot of time building a model for every problem we want to solve. And then are we really doing more work than we needed to in the first place? And so this is pointing out that these instrument-to-inference architectures are going to necessitate semi-supervised learning and end-to-end automation. And these are the two kind of driving factors for the development of a new kind of model, which is called a GAN. And I won't go into it too much, but I do want to leave up a slide. This is all for a different talk. If you're familiar with this image, this is a GAN, all right? And what we're trying to do is improve a GAN by giving it cycle consistency in a UNet vision transformer. I don't want to describe what it is, but I want to show you that we went from these models right here. You can see it's fitting to the spectra relatively slowly. We improved the speed of it by about 5 times by adding these two elements. And so we took a pre-existing version, we added in a little bit of spice, and we were able to improve the efficiency dramatically. The next step is to improve the accuracy. And all of this was done without ground truth. And so we're trying to find a middle ground between, hey, I know what I'm looking for because I have a couple samples of it, but I don't know everything I'm looking for. that's about it. Any questions?
Any questions?
I was wondering if you can talk about the uncertainties or inaccuracies from this program, because there will always be a problem for scientific paper or anything.
Oh, absolutely. Yeah, so I have an image, if it'll load, that shows the OA for some of these compared. So for example, with 200, I don't know if you can see this here, with only 200 labeled samples, right, something like traditional CNN will get less than 75% accuracy for every pixel, right? So it's clearly not going to work for a decent paper. A traditional CNN, right, you really only get decent results above 90 when you get up to 1,000 training samples, which to me is an unreasonable amount.
So that's for the supervised.
Right. For the unsupervised, we are still working on getting two-dimensional versions working. Let me just tell you, they're not accurate. So I'm working with less than 8 ground truth labels, and we're working with 16 band data. Those are the two kind of like limitations we're trying to push. And I'm unable to get even above like a 60% accuracy. And this is really, a lot of people are trying to push this technology because of the unsupervised method, being the next frontier, and because of this challenge. So I kind of see the solution being a balance between these alternately updating ones that minimize parameter spaces and something like the GON, which will take advantage of discontinuous data. The other thing that I want to look into is graph convolutions, if you're familiar with those at all. I think if you have, 1, 2, 3, 4, 5 points on this entire map, instead of those points being what your model is going to think the spatial distribution of the material is, it will know that these points are connected by a certain distance and a certain angle. And so it kind of bypasses the problem that CNNs have with spatial distribution. But that's a whole PhD thesis, I think. it's cool where we're getting with this stuff, but we're nowhere near being able to put these things up and be confident in their metrics. But generally, if you're above 90 to 95 in this range, then you can publish a paper about it and look like a real ML engineer. So that's sufficient for them.
Sorry, sort of thinking about my understanding of, well, so you talk about instrument data to inference as an onboard capability, and I'm sort of familiar with what is the current state of the art. It's like Aegis or adaptive sampling, which we use on the Pixel instrument, and they seem like pretty simple things. Where would you place capabilities like that in this universe? And then I guess sort of related, if they're sort of like the simplest version of what you're describing, what sort of computational power do you imagine flying on a spacecraft that would allow you to do something like this?
So 2 answers here. The first is that there is a major push happening in the next decade or two to put hyperspectral assets in terrestrial orbit. And that's going to have repeated reconnaissance. So like hyperspectral images, 150 plus bands updated every hour. So the kind of volume we're talking about is a communications like throughput limitation. So trying to reduce the amount of just raw data we have to send is one thing. And then the other side of things, I would say, the other half of the question would be the degree of compute. I'm not a computer scientist. I'm brand new to this stuff to begin with. But I will say that we are getting better with onboard it's FPGAs and flight computers are getting better and more power efficient. And that is the main driving factor out here, I think. So I wouldn't say like it's more of a compute problem, it's more of a power efficiency problem. And once you get to the point of these automated end-to-end pipelines, what you're really doing is selecting which portion of the pipeline you need for that kind of data. And so in the beginning, I don't think it's going to be the entire hyperspectral images is completely interpreted and all you're given is like an interpreted result. Like that's obviously the ideal a utopian future idea of this. But the reality of it is going to be you have 10,000 images and you need to figure out which you want a person to focus on. This pipeline will help you do that, right? So it'll aggregate tens of thousands of images and help you focus on which ones you need to do further reconnaissance in, whether that be for defense applications or what have you. A lot of this is for reconnaissance, defense, mining, things like that.
Any more questions?
If there's anybody out there looking to apply this kind of stuff to your research, I'm looking to learn. This has been really cool spending the last 2 months trying to, figure out what all the different words mean. And if you guys are also trying to figure out what all the different words mean, I'd love to bounce some ideas off. TensorFlow is what I got going this stuff on. It's pretty easy to set up. So I highly encourage you to just play around with it. It sounds fancy to build neural networks, but it's really not. It's the new calculator. So I would encourage you guys to start trying it out. It's pretty cool.
Can you give me a scenario where, when this is really developed, if you had a dream, like, I really want this to work out, this is where I envision it going. Can you give me a real brief scenario of acquiring data and using this tool and what the outcomes are, and how much further ahead are you?
Can I sell you a pen real quick? So we all have these beautiful devices in our hands that went from a brick with an antenna to a phone with a camera to a phone with 3 cameras. I see a future where hyperspectral imaging is in the palm of our hands. And the interpretive capabilities that can come from that requires an understanding of a deep understanding of spectroscopy can be built and embedded into these models. And so separating myself from the scientist and being more of a marketer, the future I see is one where the kind of stuff that we do with spectroscopy is coming out of our hands. And then, the example that I give people is you have a farmer who's trying to figure out what happened to his equipment. And you can take a picture of it and you can go on Reddit, you can go on Google and say, oh, I have this model, it broke down in this way. And you're looking through language, human language, to figure out what did other people do in the past. This is the start of teaching these models how to actually comprehend what's going on based on light-matter interactions. Was it a degree of heat differential between the axle and the gear? Was it because of a fume coming out of the back? The kind of things that you wouldn't really notice unless you have really, really advanced equipment. And so that's the future I see, is we're going to slowly start building these things up to make our lives more convenient. And then in 50 to 100 years, the big boys, the top 5 companies and the people that sell the stuff that all of the consumers have in their hands, they're going to be interested in this. And the thing that I didn't mention that's worth mentioning here is we're running out of training data, right? LLMs are going to be running out of unique material in the next 3 to 5 years.